some written homework. A written homework assignment from the previous class is not in my math lab. These are questions from the 7th edition of your textbook, and I typed them into your packet. So that's where they are. And we have a question on number 67. It says you decide to open a Christmas Club account at a bank that pays 6% annual interest compounded monthly. You deposit $100 on the 1st of January, and on the 1st of each succeeding month for the rest of the year. How much will you have in your account on the 1st of December? So let's see, we have January 1st, February 1st, March 1st, April 1st, May 1st, June 1st, July 1st, August 1st, September 1st, October 1st, 11, November 1st, and December 1st. Yes, because you are putting money in on that day. Yes, so you're gonna count it. There we go. Yeah, so count the December deposit. So you put $100 on each of those days. How much will you have in the account on the 1st of December? So this whole thing was about something called a fixed annuity, when you save a little bit at a time. So this is a savings account. And we have lots of formulas for savings, right? But 3 of them are for saving a big chunk of money, like where you just put in a chunk of money and let it grow and you don't touch it, right? Only 1 of them is for when you add incrementally to your account over time. And that's the fixed annuity. Savings, adding bits over time. So there's only 1 formula that applies there, and that is future value is equal to present value times, oops, copy it exactly, 1 plus little p to the capital T minus 1 all over little p. Okay. Little p, remember, is your interest rate divided by the number of payments per year that you're putting in, and capital T is the number of payments total. And capital P is the amount of your payment, right? So what are we doing? We're putting in $100 at a time. So that's my capital P. So in this one, capital P is $100. Capital T, that's the total number of payments I put into the bank account. That's why I listed this out here. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm going to put 12 payments of $100 in here. And then my little p, that's my interest rate of 0.06 divided by the number of payments I make per year, which is going to be 12. Putting this stuff in monthly, so that's 12. So maybe I'll get a number for that. 0.06 divided by 12. It's got to be 0.005, something like that. Just double check. 0.06 divided by 12 is 0.005. All right, so I've got all the information I need to plug into this formula. So I'm going to replace capital P with a 100. And then I just carefully type this all into my calculator following the order of operations. Okay, so in the order of operations, you should do what's in parentheses first. So I should add my 1 and my 0.005, and I get 1.005, right? And then the next thing in the order of operations is exponents. So I'm going to raise that 1.005 to the 12th, hit enter, and then I'm going to subtract 1, enter, then I'm going to divide by 0.005, and then multiply by 100. So over the course of the year, I'm going to end up with $1,233.55. Is that a reasonable result here? Yeah, because how much money did you put into the bank? You made a deposit of $1,200 total, $100 once a month for 12 months, but now you end up with $1,233.55 because you made a little interest. So that is a reasonable answer. If you came up with something less than 1,200, you'd know you did it wrong. If you came up with something ginormous, like $100,000, you'd know you did it wrong. So check for the reasonableness of your answer. Yes. It's the total number of payments. Yeah. Oh, yeah. So that's a really good question. This formula, applies to the situation that we just talked about. You can manipulate that formula a little bit if your last payment is earning interest, right? So in our case, the last payment is not earning interest because we make the last payment and then immediately check the balance, right? So that formula can be manipulated a little bit for the scenario where you make your last payment and it earns a month of interest. And but I'm not going to hold you responsible for that, right? So this is the only situation I'll give you. Yep. So you'll always use that formula. Yep. Okay, so number 69 from that same homework. Celine deposits $400 at the end of each month into an account that gives 4.5% annual interest, compounded monthly. At the end of 3 years, she wants to take the money in the account and use it for a 20% down payment on a new home. What is the maximum price of a home that Celine will be able to buy? Ooh, good one. Okay, so let's see how much she's going to have, right? So she's putting $400 at the end of each month into an account. So this is savings a little bit at a time. We have one formula for that, right? The one we just used. Future value is present value times 1 plus little p to the t minus 1 over little p. Okay, so this is our savings a little bit at a time formula. And we're putting $400. So capital P, that's my payment amount, is $400. Little p is my interest of 0.045. My yearly interest is 4.5%. And I need to divide that by the number of payments I'm making per year. And I'm doing this monthly, so that's 12. 12 is the most common number to put there because we do most financial things monthly. But it's not always monthly. All right, and then capital T is the total number of payments, right? And she's making payments for 3 years. So how many total payments are going to get made? 36. 3 years making monthly payments is a total of 36 payments. All right, so we're going to ignore this whole 20% down payment on a home. For now, we're just going to figure out how much money she has. All right, so I'm going to put in this stuff. First, I'm going to calculate 0.045 divided by 12, and I get 0.00375. So I have 400 times 1 plus little p is 1.00375 raised to the 36 minus 1 all over 0.00375. And then we just carefully follow the order of operations to get the future value of this account. So within the big square brackets, you should do the exponent first. 1.00375 raised to the 36 and hit enter. Then you're going to subtract 1 and then divide by 0.00375 and multiply by 400. And you get 15,000 $386.43. Does that make sense? Okay, so we just had to choose the correct formula, plug in the right numbers, and calculate. All right, so let's read the rest of the question now. The rest of the question says, she wants to use this money to make a down payment on a house, and she wants to put 20% down. There are a lot of financial benefits to putting more money down. You're going to end up paying less interest in the long run, and when you put down less than 20%, you usually have to pay like private mortgage insurance. Just means you have to pay extra money, right? So she wants to make sure she buys a house that is low enough in price that this is 20% of the total price. Does that make sense? So like, let's just say $100,000 house. What's a 20% down payment? $20,000, yeah. So quick way to get 10% is to move the decimal one to the left, and then you double it, right? So a 20% down payment is $20,000. Does she have enough to cover that? No. Okay, so she has to buy a house that's less than $100,000. So the question is, how much exactly can she afford? So you could trial and error. You could just go down from 100,000 and keep guessing. Or you could say, well, how am I taking 20% of something? What do you do to take 20% of a number? Sorry, what? Oh, yeah, you could divide by 5 or multiply by 0.2. Yeah, same thing. So we're going to let X be the price of the house, right? And we want to make sure that 20% of X is no more than what she has in the bank. So we're going to say, well, 0.2 times X, 20% of X, has to be equal to the amount she has in the bank, which was 15,386.43. And how do you finish solving this equation? Just divide by 0.2. So X, the price of the house that she can afford, if she needs that to be her down payment, is $76,932.17. It says point what? 0.20 and 0.2 are the same number, right? Oh, did I tell you how to round it at all? You're right, it does. I don't know why it's off by 3 cents. Oh, maybe, yeah. 15,386.44 divided by 0.2. There you go. Yeah, I rounded the amount in the bank. Okay, so moving into a completely different topic here, away from financial math. We have lots of group work today, so we got to get started. We're going to talk about fractals. Fractals are geometric objects defined by a recursive process. And we've talked a lot about recursive formulas. And those are formulas where you take the previous output and use it to get the next output, right? So a process in which the same procedure is applied repeatedly in an infinite feedback loop. You take your output from one step and use it as the input into your next step. So we're going to start our study of fractals with a famous example called the Koch snowflake. And we study this, and as we study this and other examples, we're going to develop some knowledge and vocabulary surrounding fractals in general. So the Koch snowflake, here's how you create it. You start with a shaded equilateral triangle, and we'll call this the seed. Just like when you have a recursive sequence, you have to start with a seed number. Here we're going to have a recursive geometric object, and we have to start with a seed shape. So we're starting with a triangle, that's our seed. To the middle third of each side of the seed, you're going to add an equilateral triangle. So each side, you're going to divide it into thirds. So you take each side of your triangle, divide it into thirds, and on the middle third, you build another equilateral triangle. And remember, equilateral means all three sides are the same length. So all three sides have to be this length. So it's going to look something like this. Right? So you add those three pieces and you get step one. Okay. So that's step one of the Koch snowflake. And then you do it again, right? To the middle third. Now you have a 12-sided figure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 sides. On every single side of the new snowflake, you build another equilateral triangle on the middle third. So just like we did with the seed, you divide each side into thirds and you add a little equilateral triangle onto the middle third. Right? And you get step two. And then you just keep doing the same thing. Now I believe you have 48 sides, and on every single side, the pointy ones and the sort of inner ones, you add another equilateral triangle. So I'd go like here, 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 here. Yeah. Yeah, every time you do it, it'll be times 4. The number of sides goes up by a factor of 4. So these are the first several iterations up through step 4. And you can see it's starting to look like a snowflake. At every step, you add equilateral triangles to the snowflake, but at some point, the triangles that you add are so tiny that it's hard to even see the changes. And to the naked eye, there's eventually no difference between one snowflake and the next. So any drawing that we make of the Koch snowflake, regardless of how many iterations we perform, will be just an approximation of the Koch snowflake. So the Koch snowflake is the shape that we would obtain if you could actually carry out an infinite number of iterations. So that means that the Koch snowflake is an abstract object, right? We can only conceive of it in our minds, and you can never actually draw it because you would have to be drawing forever, and you can't get to forever, right? However, despite the fact that this thing can't really exist, there are some things that we can know about it, concrete facts that we can know about this abstract object. Okay? Things related to its perimeter and its area. All right, so suppose the perimeter of the seed triangle was 27 units. What would you guess is the perimeter of the infinite Koch snowflake? After infinite iterations, if you were going to measure around the outer perimeter, right? So you were like had to walk this path, right? How long do you think that would be? Did I? I said we're going to do that process forever. Is that going to lead to an infinite perimeter? Maybe? Yes? No? The world may never know. We can never finish drawing it. Yeah. So the way you just used your hands to explain what you were talking about made me think that you were thinking about area, right? The space that it's taking up. Like, seems like that can't just get bigger and bigger and bigger. So the area, what gets smaller and smaller and smaller? The individual little squiggles, yeah. But are they small? Are they big enough to add to the perimeter?
Over time, if you keep doing it, it's gonna
slowly add on to the perimeter. Is it going to slowly add on to the area?
The area?
Yeah. Well, that area
Within?
within, yeah. No. Okay, so we have some good intuition going on here. Yeah.
Area inside right here is not going to change. This is
Okay, good. So we have a couple of guesses. It looks like the perimeter we think might be growing and just getting longer and longer and longer, but maybe not. But maybe some people think that this isn't going to grow fast enough. The things we're adding are going to be so small that it's not going to make a significant difference. So we have two guesses. The perimeter might be infinite, or the perimeter might be finite. Right? We might have to do some investigation to figure out what we think here. The perimeter of the snowflake. So area and perimeter are different things, right? So perimeter is the distance around. Like if you had to walk this path around the edge of the snowflake. So your perimeter, you can see, is definitely getting longer, right? If you had to walk this path, not so long, right? But if you had to walk this path and you have to go down all these little side paths, right? This is going to be a really long walk. So it does seem like the perimeter is getting longer. The question is, does it just get longer and longer and longer? Or at some point are the little pieces that we add small enough that it's not going to make a difference in our walk? Might be small like a molecule. Yeah, it might not make a difference at some point. Now, in terms of area, area is the amount of space this thing takes up. So if I kept drawing this, right, if I had to add little extra bitty triangles on here, would I ever say leave the smartboard? Would I ever run out of space to build these triangles? You think so? Yeah.
You're just modifying so it's the same size.
When you add that little triangle, you still have this little area right here.
Yeah, you are definitely always adding area. Every time you increase a step, you're adding some area. But is it just going to grow without bound towards infinity? Your triangles are so tiny, and like if I put a box around this, I'll never leave that box, even if I keep adding triangles forever. Prove it.
Because every step you're getting bigger, you're getting smaller, so it kind of counteracts.
Yeah. Every step where you add some stuff, the stuff you're adding is getting so small, right? So for area, I think it's finite. Because I could draw this all on one piece of paper. I could draw as many iterations as I want and not leave a single sheet of paper. All right, so we'll come back to these two and investigate. Question 5 still is up in the air. Yep. All right, so self-similarity. This is a property of many fractals, including the Koch snowflake. It means that the object is similar to part of itself, which in turn is similar to an even smaller part, and so on, right? So in other words, if you zoom in on a small piece of the edge of the snowflake and blow it up, it looks exactly like the original snowflake. And you can do this forever, right? Take this zoomed in piece, blow it up, looks exactly like this piece and the original. Okay. So we're going to check out this short video clip from YouTube. If you get motion sick, you might want to shut your eyes. Where's the... So we're just zooming in on the Koch snowflake over and over and over again. So many fractals exhibit this property of self-similarity. In the case of the Koch snowflake, the self-similarity is infinite, meaning you can zoom in forever, right? Obviously, in the video clip, they had to stop eventually. You can't watch an infinitely long video clip. But universal, which means you can pick any part of the snowflake, right? I could zoom in here or here, doesn't matter, right? I can zoom in on any part of it, and it will always look similar to the original, right? And exact, meaning it looks exactly the same. Right? Now, lots of fractals and self-similarity exist in nature, but in practice, self-similarity can't be infinite or exact, like it is with a theoretical thing like the Koch snowflake. Yeah, question? Uh-huh. Mm-hmm. It's okay. It's okay. So you see fractal forms in nature and biology all the time, and for good reason. Fractals allow for once we study the area and the perimeter a little more in depth, you will see that fractals allow for a large distance to be covered, to have a lot of exposed stuff in a small space. Yeah.
Right, so then I guess I'm getting at, we started working with smaller, so then these are basically adding on to that.
Sometimes. If the molecule is a small version of the whole, then that would be a fractal. Yep. Yep. So, like I said, in practice, self-similarity can't be infinite because everything that exists in the real world is finite, right? So you can't zoom in forever. And it's not exact because we always have small variations in the real world. But these are some examples of things that grow as a fractal in nature. So I have a fern here, and the whole fern looks similar, right, to a little piece of the fern. If you pull that off, it's a miniature fern, right? And each little leaf on the branches is like a little tiny miniature fern. And then if you look at the veins in those leaves, it looks like a little miniature fern. Yeah. So you can zoom in 3 or 4 times, but then that's it, right? This is a kind of cauliflower, I believe, that grows in these little florets. And if you zoom in on one of those little florets, yeah, yeah. If you zoom in on one of those little florets, it looks just like the whole, a miniature version of the whole.
It's related to like the conscious.
Yeah, yeah, because the spirals that we see form in when we use Fibonacci numbers create self-similarity. Yeah. This is a fiddlehead fern. These grow in the wild and are edible, right? Yeah. So you can see that the whole fern is this big spiral, right? But then it has these little tiny spirals on it that are miniature versions of the whole. And within those are little tiny spirals that are miniature versions of the whole. And then this is the coastline of, I want to say Florida, I don't remember. So in this case, we consider it a fractal, but it's not exact. The self-similarity isn't exact. But if I were to say zoom in on this chunk of the coast, you wouldn't be able to tell which picture is which, right? You would say, well, they're both, an aerial shot of a coastline. They'll look similar to each other. And then anything that branches, right, is also a fractal. Because if I just look at one little branch of the lightning, it looks similar to the whole thing. All right, so we're going to investigate first the area of the Koch snowflake. All right, so I'm going to have you, I will get you some crayons. And you're going to draw the Koch snowflake, and as you draw each iteration, you're going to keep track of the area of the Koch snowflake. All right, so the first thing we're going to do is draw a seed triangle. So I'm going to pause here and get you crayons so you can follow. All right, so let me just walk you through the first few steps and then I'll let you finish on your own, okay? So on the triangular grid paper that you have on the next page, you're going to create a seed equilateral triangle where each side is 9 units. All right, so I should make this smaller so I can fit it all on one page. Okay, so I'm going to create a seed triangle that is 9 units on each side. I'm going to try my best to draw it in the middle of this paper. So if I have my top there, I got to count 1, 2, 3, 4, 5, 6, 7, 8, 9 units down. And then 1, 2, 3, 4, 5, 6, 7, 8, 9 units. And connect.
Oh. So you're trying to center it in the
I just wanted to make my seed be in like the middle of my paper. Doesn't have to be exact, just to give myself room to draw. Yeah. All right, so then you're going to shade this, right? Color in this triangle. And I need to know its area, right? Oh, sorry, we're looking at the perimeter first. So we need to write down stuff about its perimeter as we draw. Okay, so the seed has 3 sides. The length of each side was 9, which means what's my perimeter? 27, yeah. 9 plus 9 plus 9. It's a distance around. You can do 3 times 9 and you get 27 is the perimeter. All right, so then we go on and try to draw step 1. So on the middle third, which means I have to divide each side into thirds, and on the middle third, put a new triangle. So each side is 9, so a third of 9 is 3. So there's 3, and if I put an equilateral triangle on this piece here, all 3 sides have to be the same length, so they all have to be 3. And I've put an equilateral triangle on one side. So there's another one, and we shade that in. And one more, shade that in. So now, how many sides does my Koch snowflake have? 12, yeah. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And what's the length of each side? 3. Okay, so we go back to our table and we say we now have 12 sides. Each side has length 3, which means what's my perimeter? 36. 12 times 3 is 36. All right, I want you to continue. Draw at least 1 or 2 more iterations and write down the perimeter and see if you can write formulas, right? Recursive or explicit for the number of sides, the length of each side, and the perimeter. All right, so let's go over some of our results. All right, so with our next step, we have to look at all of our 12 sides and add a triangle, an equilateral triangle, onto the middle third. So if I take 1/3 of 3, right, the middle third is just going to have length 1, and I have to put a little triangle on every single side of my existing snowflake. All right, good. So now how many sides do I have to my triangle? 48, and we should count them. So let's see, we go. I'll do it in another color so we can keep track. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44. You're right, I did. It's 48. We'll trust you guys. Yeah. So there are 48. Each side has length 1. So the perimeter is 48, right? And when I do the next step, I'm going to have to, I have to break my triangles into thirds now. So on each triangle, I'm going to have to put a little baby triangle on each side. So cute. All right, so after I do that, how many sides am I going to have? 192. And each side is going to be a third of 1, right? Because we took 1, we broke it into thirds, and we put the triangle on the middle third, so it was 1/3. And 192 times 1/3, what is that? 64. Oh, then you must have rounded something like.
1 divided by 3 times.
So 1/3 is the exact value. If you used a decimal estimate for 1/3, because shh, quiet. 1/3 as a decimal is 0.3 repeating forever. So if you used 0.3 or 0.33 or stopped writing 3s at any point, you get an estimate. But instead of multiplying by 1/3, we could just divide by 3. It's the same thing, and you get 64. Yes, it's not. 192 times 1/3 is exactly 64. All right, so I don't really want to draw anymore, right? Because my triangles are now going to be so tiny. So I'm hoping that we can see a pattern here without having to draw any further. So anyone see a pattern in the number of sides? Times 4. 3 times 4 is 12. 12 times 4 is 48. 48 times 4 is 192. So 192 times 4 is 768. And anyone see a pattern in the length of each side? Divided by 3 or multiply by 1/3, same thing, right? So what's 1/3 of 1/3 as a fraction? A ninth. 1/3 of 1/3 is a ninth. Because the word of means multiply, right? 1/3 times 1/3 is 1/9. Okay. Then you multiply these together, 768 times 1/9.
Right, now we get outside of the.
Yeah.
numbers, right?
Yeah, so now we're going to start getting some decimals. When you see 0.3333333333, what is that? That's a third. This is 85 and 1/3. If you want to be exact, you got to write it as a fraction. Yeah.
What about the next? Oh, I know the answer. Perimeter.
Yeah. So I didn't ask you to do another one, but if I wanted to write formulas, right? First, let's just look at the perimeters. 27, 36, 64, 85 and 1/3. What's happening to these perimeters at each step?
We're going at a slower. Right?
27 to 36, that's an increase of 9. And then 36 to 48, that's an increase of 12. 48 to 64, that's bigger than 12. So they're growing by larger and larger amounts, right? So do you think that what's going to happen to that perimeter as we just keep adding more and more iterations? It's just going to get bigger and bigger and bigger. That thing's going to just grow without bound to infinity. So we answered our first question about perimeter. It's just going to grow towards infinity.
Is there a sequential pattern?
Yes, we can definitely write formulas for these things. So let's say in this one, I can write a recursive or explicit, right? For recursive, I would say, well, this is M, my list, I named this list M. So this is M1, M2, M3, right? Remember back to our sequences stuff. So M sub n, right, is always equal to 4 times the previous number in the list. And what was my notation for the previous number in the list? M sub n minus 1. So that's a recursive rule. If I wanted to write an explicit rule, I would say, well, I start at 3 and I multiply 3 by 4 over and over again, n times. And repeated multiplication is expressed with an exponent.
Would it also work if you did n minus 1?
No, it has to be m sub n minus 1. Because n minus 1 times 4, so if I wanted to know m5, you're saying that that would be equal to 5 minus 1 times 4, which is 16.
Well, I just got confused because n is in this step. Like n to the left of the equation.
Oh, yeah, that.
The numbers are represented by m. By n.
Yes, the step, the iteration that we're on is the nth iteration, yeah.
So the nth iteration minus 1 times 4.
Yeah, and the way we notate that is m sub n minus 1. That's the iteration before the nth. Yeah. All right, so I want to look at my length of each side and write that as a formula. And I named this list L, so this is L1, L2, L3, right? And so L sub n is always equal to a third of the previous number in the list. So 1/3 times, right, because of means times, 1/3 of the previous number in the list. So the previous number in the list would be L sub n minus 1. All right, and if I wanted to write this explicitly, I would say we'll start with 9 and multiply by 1/3 over and over again, which you notate with an exponent.
Would it be okay if you did it for the first one? Also then
L sub n minus 1 divided by 3. Yes. Yep, you could do that. The same thing with this one. You could write this as 9 divided by 3 to the n. Same thing. All right, so for the perimeter, we're looking at the number of sides times the length of each side, right? So to get the number of sides, you multiply by 4, and to get the length of each side, you multiply by a third. So 4 times a third, what is that? 4 times 3 is 12. What's 4 times a third? 4/3. Yeah. 4/3. So let's look at the number 4/3, right? If you multiply 27 times 4/3, and again, that 4/3 comes from the fact that the number of sides is going up by a factor of 4, while the length of each side is going down by a factor of a third. So 27 times 4/3 is 36. Times 4/3 is 48. Times 4/3 is 64. Times 4/3 is 85 1/3. So what kind of sequence is this? Exponential. This is exponential growth or a geometric sequence. Yep. So every term in this list, P sub n, the perimeter at step n, is 4/3 times the perimeter at the previous step. Or if I wanted to write this explicitly, I would say P sub n, my perimeter starts with 27, and you multiply by 4/3 n times. All set? Okay, good. So So looking at this formula for the perimeter, it's exponential growth, right? And I'm multiplying over and over again by the number 4/3. Is 4/3 bigger than or less than 1? Bigger than 1. When you multiply something by a number bigger than 1, does it get bigger or smaller? Bigger. So I'm multiplying by 4/3 over and over again, which means the perimeter is just going to get bigger and bigger and bigger. So I did this in the table. And I did this in the table. And recursive, I did this in the table. So if I wanted to calculate the perimeter of the 10th step of the Koch snowflake, right, I would say, well, P sub 10 is 27 times 4/3 to the 10th, right? I can use my formula that I wrote. And see, 27 times 4/3 to the 10th is 479 point, we'll just say 5. Really long. Much longer than the original triangle, was just 27. Yes.
So why is the area not as small?
That is a great question. The perimeter is growing to infinity. How is it possible that the area does not? We're going to investigate the area in just a couple minutes. Okay. Mm-hmm. Yes. Yeah, that's a good way to think of it. So the perimeter of the actual Koch snowflake after infinite iterations is infinite, right? All that means is that as you add iterations, the perimeter just gets bigger and bigger and bigger without bound. Just grows forever. Based on our conjectures about the perimeter of the Koch snowflake, probably some of you are surprised and some of you are not, right? Depends on what you guessed to begin with. Okay, so now I want to think about the area. So it did seem that the area was finite based on the fact that you can keep drawing more and more iterations and you never will leave your piece of paper, right? And that piece of paper has a finite area. All right, so in order to study the area of the Koch snowflake, it would be helpful to be able to calculate the area of an equilateral triangle. And I have a formula. So what's the typical formula for the area of a triangle? Yeah, so area is usually written as 1/2 base times height, right? And this would be your base, and your height is a line perpendicular to it, right? This is an unhelpful formula for this guy because I don't know the height, right? It's not s cubed. Nope. Nope. That would be the perimeter. Yeah. So I have a special magical formula that you're typically not taught in school. Because usually you can get away with this one. If you know a little trigonometry or geometry, 30, 60, 90 triangles, you can figure out the height. But we're not going to do that. I'm just going to give you my magical formula. If you have an equilateral triangle where all 3 sides are length s, its area is s squared times the square root of 3 divided by 4. So this is the formula we're going to use because all of the triangles that make up the Koch snowflake are equilateral. So if you know the length of each side, you just square it and multiply by √3/4, and you get the area. So for example, let's say I've got this triangle and its sides are length 10. Right? I want to find its area. I just replace the s in that formula with a 10. So it would be 10 squared times the square root of 3/4. So that's 100 times the square root of 3/4. And 100/4 reduces to 25. So this is 25 times square root 3. And then if you want a decimal, you can put this in your calculator. 25 times the square root of 3. And you get about 43.3. Yeah, so no, that's your area. It's not height, that's the area. Yeah. Yeah, so typically when you usually for most of you in all of your previous math lives, you used 1/2 base times height to find the area of a triangle. I'm giving you an alternate way of finding it that works only for equilateral triangles. But because that's the only kind of triangle we're dealing with, this is a helpful formula for us. All right, so does that make sense? They will come out the same. So if I do 100 times the square root of 3 and then divide by 4, I get 43.3. Yep, side squared times square root of 3 over 4. Oh, no, sorry, that's S for side length. All right, so I'm not going to have you do this. I'm going to walk you through. We're going to skip straight to the punchline here. All right, so this is tedious. So I'll do a couple of steps, and then whenever you have tedious math things that are a big table like this, what's a great tool to use to do all of it for you? Excel, yeah. Okay, so I have first 2 done here, and I'm investigating the area, right? So the area of the seed, if each side has length 9, then you just do 9 squared times the square root of 3 over 4 to find its area, right? So I would do 9 squared times the square root of 3 divided by 4, and that's 35.07, right? So that's the area of my seed triangle. I only have one triangle right now. That's what that one is. Its area is 35.07. There was no previous area. This is my first triangle, so that's my total area added to the previous. So the area of the snowflake at this step, when I round to 1 decimal place, is 35.1. All right, so then for the next step, right? When I do the next step of my triangle, oops, it would be helpful if I draw this, right? I get to keep all of the area I had before, and I have to add to that area 3 new triangles. Turn that down, please. I can hear you. I have to add to that 3 new triangles. And each triangle has side length 3, right? This is 3, 3, 3. So the area of each triangle would be 3 squared times the square root of 3 over 4, which is approximately 3 squared times the square root of 3 divided by 4, 3.89 about. Yeah, but I have 3 of those, right? I attached 3 triangles. Each one has area 3.89. You multiply those. I have 3 triangles, each with that area, multiply them together. Yeah, and then you have to take the previous area, add it to these new triangles that you just attached, and you get your new area. Right? So you see how I'm building the table?
So to get 11, you get 3.
Times 3. So in my next step, the side length of each attached triangle would be 1. How many triangles do I attach? 12. Yep. And then the area of each attached triangle would be 1 squared times the square root of 3 divided by 4, which is by about 0.433. Right. Yep, the side length is 1, so you can get the area of an equilateral triangle is length 1. But I'm adding 12 of those, so I'm going to multiply that by 12. And I would get, so I multiply those together, and I get 35.196. And then add that to the previous area I had. So I would add that to 46.8, and I get 51.99. Okay, before I even show you a whole big Excel spreadsheet with this in it, what do you notice about the jump from 35.1 to 46.8 versus the jump from 46.8 to 51.99? Smaller, right? So I did grow, right? Because I added some area, but I grew by a smaller amount in the second step than in the first. All right, so I have to find that Excel spreadsheet. All right, here's a picture of my Excel spreadsheet. You'll see the first 3 rows look exactly like what we just did, except I've added a column. You can ignore this last column at first. But my first 3 rows, I have the 35.07, the 46.7, 51.96, except the beauty of Excel is that I don't have to round anything, right? I've kept these numbers all perfectly exact. And I took this Excel spreadsheet down to 22 iterations. Okay. So what do you notice about the area? Remember, this last column is the area of the snowflake. It's barely changing, right? It's once it hits 56, it just is growing so slowly that it's never getting bigger than 56. And here is the crazy thing. Over in the next column, I decided to do a ratio. Don't ask me why I did this. I took the area at any given step, right? Any given step, so like this guy, right? And I divided by the area of the seed, which was the original area, right? Area at any given step divided by the area of the seed. And look at this ratio. At some point, it just becomes 1.6 and stops changing. Yeah, 1.618 is a number we're familiar with. This isn't 1.618, it's just 1.6. Yep. Yeah, the more iterations we do, so I'm carrying so many decimal places here, that when a decimal place changes way out in the millionths place, it's not affecting my 1.6 ratio at all. So what happens, my big conclusion here about the Koch snowflakes area, is that after infinite iterations, the Koch snowflake, its area is just 1.6 times the area of the seed. So despite the fact that we can never finish drawing it, we know that the area final, right, is 1.6 times the area of the seed.
I know that's not 1.8.
Yeah.
But we have some relation.
No. Yeah, it's not the number phi, it's 1.6, which is a rational number. Yeah. Yeah, and this thing that we built is not natural, right? This is a abstract man-made thing. Hold on. Let me just make my last conclusions about the Koch snowflake are written here. Quiet, please. All of your formulas that we discussed today are written here for the number of sides, the length of each step, the perimeter at each step, that the perimeter is infinite and the area is finite, 1.6 times the area of the seed. And that's it.